So we'll discuss today one of the very important one, although it looks very simple one. Most of the people don't teach this one, right? Hardly they spend 1 minute for this one. Isomers are broadly classified as structural isomers and stereoisomers based on the change in connectivity of atoms. Here, how that change in connectivity of atom takes place, that is further basis of classification of structural isomers. If that change in connectivity of atoms, the way atoms are connected to each other, the way atoms are connected to each other, this is the basis of further classification of structural isomers. And here, if that time, that change in connectivity of atoms cause the change in position of an atom or group of atoms or double bond in triple bond, in that case we say position isomers. So you can say position isomers are caused due to change in position of an atom or group of atoms or change in position of double bond or triple bond. Yes, this is very simple one and it's not difficult to understand, honestly speaking. But few things what we should keep in mind, that you see first. Here if I say that CH3, CH2, CH2Br, yes, one bromopropane, and if this Br is changing its place and that becomes 2 bromopropane, yes, here the change in connectivity of atoms appear as a change in position of an atom Br. These two are position isomers. True? No problem. This is correct. But at the same time, if we take here the change in position of CH3 group, CH3 group is also the substituent, right? No? As I said there, you see this example also, simple example. I just take here very simple example. CH2, 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 and here the OH. This is the group of atom OH, functional group. This time this one is butane 1-ol. If we change its position, yes, we say this one is CH3, CH2, CH, OH, and there the CH3. Certainly, we say position isomers, butane 2-ol. Here, what we need to take care that when this kind of change in position of an atom or group of atom is affecting the parent chain, then no more position isomers. Correct? If that change in position of an atom or group is affecting the functionality. Functional group itself is changed. No more position assumes. These 2 points are very important, right? So, for example, just I take one more example. Here only. We take CH3, CH, CH3, CH2, CH3. This one is, let's take here one more. Let's take here one more carbon. CH2, CH3. This one is 2-methyl pentane. We take here now CH3, CH2, CH, CH3, CH2, CH3. What are these two? Certainly. This one is 3-methyl pentane. What are these two? 2-methyl pentane. Here, this is the substituent group of atom which is changing its place from this second place to third place. These two are position assumes. No dot at all. Now we are changing the position of the same group, CH3, CH2, CH2, 1, 2, 3, 4, 5, CH2, CH3. We take this methyl group to this first place, so-called first place. What do you think now? Is it the change in position of that group? Yes, no doubt. That is a change in position of that group only. Methyl group is shifted from this position to that position. This is a change in position. But this is no more position isomer. Because that becomes the integral part of the chain, and the parent chain is getting affected. So this one is no more position assumes. Then what are these two? If you compare, if you say this one is 1 and this one is 2 and this one is 3, so what about the 1 and 3? 1 and 3, these two are chain isomers, not position isomers. Correct. Here I take few more examples where you will understand this part better. Okay? Take this one. I take here, let's take here this example. This example you take. In this case, you see, there is, this one is, there is OCH3 and some methoxy group is there. And you see this one, that in this case, this methyl group, the position of this methyl group is changed from here to there. Now it is here. 1 and 2. Methyl group position is changed. Now what do you think? Is it really the change in the position of methyl? Yes, this is change in position of methyl group. But this is no more position isomer. It is not the case of position isomerism. Because due to the change in position of this methyl group from oxygen to carbon leads to the formation of, leads to the change in functionality. This is no more ether. This one is no alcohol. So 1 and 2 are functional isomers, not position isomers. So here 1 and 2, what are these two? Functional isomers. Very good. Functional isomers. Good. Nice. What about 1 and 3? This is OCH3, OCH3. Sir, this one 1 and 3. 1 and 3. This one is branched. Chain isomers? Think. Chain isomers? No. Let's analyze properly. This is the mistake-prone example. In this case, most of the students in flow commit mistake. So here, when you analyze this one, that very first you should have clarity that what molecule has been given. In this case, molecule is 1, 2, 3, 4, 5. This one is methoxypentane, 1-methoxypentane. And here what you branch, you see, this is not actually branch. Actually here, also when you analyze, this one is the chain only. 1, 2, 3, 4, 5. Where there is change in chain? There is no change in chain. There the 5 carbon atoms, here also 5 carbon atoms. Then what is the change? Change in position of OCH3. Yes. This one, first 1-methoxypentane, third one 2-methoxypentane. And so 1 and 3, these two are certainly position isomers. Correct. What about 1 and 4? It looks very similar, but very similar to 1 and 3. Analyze it properly now. There also, in very first move, we find that methyl group is there. Here also methyl group, but this is the different case. In this case, when we analyze this structure, we observe that there is a different chain. In this case, chain starts from here. This is 1, this is 2, this is 3, this is 4. The parent chain itself is changed. OCH3 is there only, but the parent chain is changed. 1 and 4. There the 5 carbon atoms are in the chain, and in this case, only 4 carbon atoms are in the chain. Then, what are these two? 1 and 4. As here the parent chain basic skeleton of the molecule is changed, that's why these two are chain isomers. These two are chain isomers. What about 3 and 4? 3 and 4, that is also there. I have given 3 and 4. 3 and 4. Same. This one, 1, 2, 3, 4. Chain is of 5 carbon atoms. In this case, chain is of 4 carbon atoms. So as it contains 5, it contains 4. So there is basic difference in the chain, basic skeleton of the molecule. That's why these two are also chain isomers, right? Chain isomers. What about 1 and 5? There also you find that there is one carbon atom is changing its place from this side to that side. Actually, that is the way connectivity changed, and you need to notice that change in connectivity is basically the change in, mostly you will find that change in position, but that every change in position is not causing position isomerism. This case also, when one of the carbon atom is shifting from one side to other side, nature of alkyl group is changed. This is no more methoxy. This one is the ethyl group, so it is ethoxy. That side we have 5 carbon atoms pentyl group. This one is now having only the 4 carbon atoms, butyl group. Nature of alkyl group across this kind of functional unit oxygen in this ether is changed, and that leads to metamerism, right? So these two are metamers. These two are metamers. With these examples, in this context of position isomerism, I want to say that every change in position is not the basis of position isomerism. This is one of the examples, and some of the examples are very close. At the same time, some of the examples you find significantly different. That is true. Let's take here one more example of the similar kind, right? You take here one more example of this kind. You take this example. Take here this example. This one is 1, this one 2, this one 3, this one 4, this one 5 and 6. This one is hexa 1, 4 diene. Hexa 1, 4 diene. Good. First, this one you say hexa 1, 4 diene. When we analyze the next structure, we find this one is 1, this one 2, this one 3, this one 4, this one 5 and 6. This one is hexa 1, 3 diene. And in this case, this one is 1 and 2, 3, 4, 5 and 6. This one is hexa 1, 2 diene. 1, 4 diene, 1, 3 diene, 1, 2 diene. Oh, so nice. It sounds very nice. Very apparent, very clear that 1, 4, 1, 3, 1, 2 position isomers. Is it true or not? 1 and 2, no doubt, position isomers. But 2 and 3, 1 and 3, 1 and 3, no more position isomers. These two are functional isomers. These two are functional isomers because this time that change in position of double bond is not directly affecting the functionality of the group. This one is cumulene. Sir, how to know that with that kind of change, functionality is changed? You can notice. Here, hybridization is sp2. There sp2. There sp2. There sp2. Here sp2, 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 sp2. Here sp2, there sp. Complete arrangement is changed, and that is affecting its reactivity, stability. Entire set of properties are changed. Functional group is an atom or group of atoms which is characterized with a set of properties. And yes, when we have this kind of setup, entire set of properties are changed and it is recognized as one of the functional group, different functional group, and that is cumulene, and that's why 1 and 3, these two are no more position isomers. 1 and 3 are functional isomers. Functional isomers. And same, likewise, 2 and 3. Hexa 1, 3 diene, that is truly diene, and hexa 1, 2 diene, cumulene, and so functional isomers. So functional isomers. Yes, We have to be careful. We have to be careful in this thing, you will enjoy. Let's take here one more example. Take this example. 1, 2, 3, 4, 5, 6. Cn is there. That Cn is here. That Cn is here. What are these two? 1 and 2. What are these two? Sir, so clear now? Change in position. Position isomers. These two are not position isomers. These two are not position isomers. Then what are these two? Let's discuss. Here, we should not think that it is like this. Here the substituent is not Cn. It is a functional. It is a part of the chain. And when you write like this, these two are chain isomers, not position isomers. Because if you analyze it properly, then you'll find that the basic skeleton, basic chain is here. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. No, this one 1, 2, 3, 4, and 5. Here the substituent is methyl group. Here the substituent is methyl group, not Cn. And now, due to the change in position of Cn, the substituent is no more methyl. This one is ethyl. Due to the change in position of this Cn from this place to that place, basic skeleton is changed. Now, there are only 5 carbon atoms in the parent chain. Yes, so 1 and 2 are chain isomers. Okay, this is the point what I need to bring in your notice, and very, very clearly that every change in position of group is not the basis of position isomerism. You see this? It is Cn. But here, what you need to notice and you need to remember that carbon containing prime functional groups like COOH, like COOH, like C double bond O, OR, like C double bond O, X, C double bond O, and H2, like C double bond O, H, C triple bond N. These functional groups, carbon containing prime functional groups, sorry, you cannot change the position of these groups when these groups are the main functional groups. You cannot change, because the carbon chain starts with the carbon atom of these functional groups. So if you change the position of these functional groups, that is directly affecting main chain, basic skeleton, parent chain of the molecule is changed, and with that one you will get chain isomers, not position isomers. You can change. First you see this one, CH3, CH2, CH2, CH, CH double bond, and CS3. If we change the position of the CHO from here to there, CH3, CH2, CH, CH double bond O, CH2, CH3. What are these two? These two are no more position isomers. These two are chain isomers. Again, don't misinterpret my statement. I said when these groups are prime functional group, that time you cannot change to get position isomers. You can change. You can change. For example, I am giving one example. Take this example: CH3, CH2, CH, CHO, CH2, COOH. Now you see this one. In this condition, if you write here now CH3, CH, CHO, CH2, CH2, COOH. This one and this 2. What are these two? 1 and 2. What are these two? Here also you are changing the position of CHO. This one is 1, this one 2, this one 3, this one 4 and 5. This one is 1, this one 2, 3, 4, 5. You are changing the position of CHO. Position isomers. These are position isomers because CHO is now carbon containing functional group but not prime functional group. And that's why in this condition its position can be changed because this is a normal substituent. It is not the part of the parent chain. That time you can change. I hope you got it. Correct? Good. We will discuss here the other aspect of this position isomers, that is number of position isomers. This is also important. Questions are asked like this. Find the number of position isomers. One misconception I am telling you. You see this. There is one question. CH3, CH2, CH2, OH. Question is how number of position isomers for this molecule. Then we say that 2, sir. Most of you are saying 2 only, but not 2. You know the correct answer, but your answer is wrong. This one is propan 1-ol. A position isomer of this one is propan 2-ol. So there is only one isomer for this one. Here, you should not think that it has 2 isomers. Position isomer of this, position isomer of propan 1-ol is propan 2-ol. You can't say position isomer of propan 1-ol are propan 1-ol, propan 2-ol. No, you can't speak like this. So for this one, position isomer will be 1. Number of position isomers 1. Propan 2-ol. If the molecule has been given, then excluding that you have to say when you are dealing with structural isomers. At the same time, when you are dealing stereoisomers, include that. Whatever given in front, include that also. But for structural isomers, we don't. Okay, I hope you got it. In this case, what? CH3, CH2, CH. Very simple question. Here we have two chlorine atoms, CHCl2. So this is one dichloro. This one is one dichloro. Position isomers? Yes, you can write 1, 2 dichloro. You can write. Good. And even you can write here the 1, 3 dichloro. You can write 2, 2 dichloro. Will you write 3, 3? You can't. Because 3, 3 is actually 1, 1. Right? So you cannot write. So position isomers of 1, 1 dichloro 3. 1, 2, 1, 3 and 1, 2, 2 dichloro. Here there is inertial mistake. My purpose is not to teach you what is the correct answer, but how to make answer correct. Right? That is also my responsibility. And so the question is there, number of position isomers 4, mono substituted benzene. Immediate answer. Benzene na? Yes sir. Sir, ortho, meta and para sir. Most of you, not everyone, don't listen the question. Immediately you get connected with the benzene. And then you start counting ortho, meta, para. But it is a case of methyl or mono substituted when only one substituent is there. In that case, whether you keep here or there or there or here or there or there, wherever, all places are equivalent. In this case, where is the ortho, where is the meta, where is para? Ortho, meta, para, these are considered for di-substituted one. This is the common mistake that I am telling you. You might be doing correct only. Your answer may be correct, your approach may be correct, but in flow, most of the students do this wrong. This way. So you need to be careful that I am telling you. Okay? On the same pattern, I am asking another question. Number of position isomers 4. Mono substituted naphthalene. Answer please. Mono substituted naphthalene. Now, how to answer? Here, one thing what you need to understand. In naphthalene, there is one fixed system of numbering of carbon atoms. This carbon atom is considered 1, 2, 3, 4. These are not numbered. This one is 5, this one is 6, 7, 8. Now, if there is substituent on this first place, or on this fourth place, or fifth place, or there the eighth place. All these places are equivalent places. Which are equivalent? 1, 4, 5, and 8. All these are equivalent. If this methyl group is kept on the 4th, then also we say 1 methyl naphthalene. This is also called alpha. If you keep on the 5th position, then also you say 1 methyl. If methyl group is here, then this is 1, this is 2, this is 3, 4, 5, 6, 7, If this is on the 8th place, then this is 1, 2, 3, 4, 5, 6, 7, 8. So all these places are equivalent, and so this set means 1. And if that one is there on this place, second place, third place, sixth place, or seventh place. So 2, 3, 6, and there the 7. All these are equivalent sites. All these are equivalent sites. In that case, whether you keep this substituent on the second place, certainly will say 2-methyl. If you keep on the third, then also you will say 2-methyl, because that time this one is 1, this one 2, this one 3, 4, 5, 6, 7, 8. If you keep that methyl group on the 6th place, then this one is 1, this one 2, this one 3, 4, 5, 6, 7, 8. If on the 7th, then this one is 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 6, 7. All these are equivalent, and that is called beta. So, for question is there. Notice, for mono-substituted naphthalene, 2 Poisson isomers, alpha and beta, 1 and 2. But if the question is there for 1-methyl naphthalene, number of Poisson isomers for 1-methyl naphthalene, 1. 2-methyl naphthalene. Correct. Yes. Like that, I am giving one more question. Interesting question. I hope you will enjoy that question. Okay? That question is, here I am just extending that one. Okay? You see? This one is anthracene. For mono-substituted anthracene, number of Poisson isomers. This has also one set system of numbering, right now. This one is numbered 1, this one 2, this one 3, this one 4. These two are not numbered first. This one 5, this one is 6, 7, and 8. Either you say this one 9, that one 10, or 9 and 10. This is the way all these carbon atoms of this anthracene are numbered. This one is anthracene. How in this case? In this case also you have the 3 set of Poissons. If the substituent is there either on the 1 or 4 or 5 or 8, all are 1. 1, 4, 5, 8. All these are equivalent sets. We say alpha. All these are equivalent sets. And whether you keep the substituent on the second or the third, if on the third, then also 2. On the 6th, then also 2. On the 7th, then also 2. If there is only one substituent, either on 2 or 3 or 6 or 7, we say 2 only. So these all are equivalent sites. 2, 3, 6, 7. We say this one beta. 9, 10 different. And if you keep on the 9 or 10, both are different from the rest of the 2. We have the 3 set of equivalent places, and so number of Poisson isomers for the mono-substituted anthracene will be 3. Will you try one more? Try. I am asking here, for phenanthrene, number of position isomers for the mono substituted phenanthrene. You know, this has also one system of numbering, and this is called 1, this one 2, this one 3, this one 4. These two are not numbered. This one 5, this one 6, this one 7 and 8, this one 9, this one 10. This is the way these carbon atoms are numbered. So in this case, what we find that after 1, this carbon and that carbon, and then again 8. But when we take here the 4th, after the 4th we have this common, but after that we have the 10, 9, and then again this carbon comes. So these two places are not symmetrical, because back to back you are getting here, there that common carbon atom, but in this case we don't have. That's why these two places are not equivalent. In this case we have more. Then which are the equivalent places here? Yes, you see 1 and 8, these two are equivalent. 2 and 7, these two are equivalent. 3 and 6, these are equivalent. 4 and 5, these are equivalent. And 9 and 10, these are equivalent. How many set of equivalent sites we have in the case of phenanthrene? 1, 2, 3, 4, 5. So for the mono substituted phenanthrene, 5 position isomers. That's the answer. Here it's matter of approach. You need to have clarity. Right? You know, position isomerism is taught in 2 minutes, 1 minute. And later when the question comes, they do mistake, certainly. Right? We must learn in detail, right approach. Okay? Thank you. I hope you learned it. Okay? Enjoy.